So I'd like to talk about the way in which rifted basins and margins are affected by convective processes. And so to start with, I'll just say I'm taking a strictly observational perspective and, in a sense, a sequence stratigraphic perspective. And the second thing is I'm going to confine my comments to 3 examples of the way in which post-drift thermal subsidence has been dramatically modified by convective processes. Okay, so our understanding of how rifted basins and margins work has been now around for a long time. So many of us are concerned with the way in which accommodation space is developed and how the structure at the base of sedimentary basins and margins grows, how that affects the stratigraphy, and then how that affects heat flow and maturation. And the name of the game is about how to quantify observations and then fit observations with simple theory. And it really goes back to the work of Dan McKenzie in the late 1970s. So the elephant in the room in this endeavor is summarized by this rather splendid cartoon that Jean Braun, your colleague, drew some years ago, which shows you the way in which Stokes flow within the viscous mantle produces positive dynamic topography when you have low density material at depth, and negative dynamic topography or subsidence when you have high density colder material at depth. Now, the best place, if you want to try and make precise observations of dynamic topography on Earth, a really good place to start is the oceans, because we have a very simple rule as to how ocean cooling due to the which gives rise to the thickening of the oceanic lithosphere, how that occurs. So it's quite easy to interrogate age depth information in the oceans to isolate positive dynamic upwelling and negative dynamic downwelling, which are essentially residuals on the age depth profile, as you will see in a moment. Now, the key to being able to do this accurately, because we've been able to do this correction really since the work of Bill Maynard in the early 1970s, but the key is having really detailed, splendid seismic profiles like this one. This is an industry line, and the key thing is we can see the sedimentary section in all its glory down to top basement, and we can also see the oceanic moho. That unlocks our ability to make very precise corrections for the isostatic effects of the sedimentary pile and the isostatic effects of oceanic crust being different to about 7 kilometers thickness. There's a lot of such data. Some years ago, Mark Hoggard and I put together a database of over 2,000 measurements of what we regard as accurate age depth measurements. Since that time, Megan Holt has been working with me, and we've now built it up to over 10,000 observations. The story I'm going to tell you today hasn't changed in any detail. So you can fit an optimal plate model to those observations, which is the red line. And then the name of the game in terms of constraining the maximum that dynamic topography can be in the oceans is to measure residuals. So we can have a positive residual where at a given age, 100 million years, this point here sits at least a kilometer above the age depth cooling curve. So that's a positive residual depth anomaly. And equally, you might have a point over here, which sits below. So in this way, we can map the oceans in terms of residual depth anomalies, which we can take as a proxy for the maximum that dynamic topography can be in the oceans. So that leads us to this map here. And we're in the middle, in fact, of producing a pretty dramatic update of this map, both in terms of ocean coverages and critically in terms of continent coverage. But I'll confine my words to this already published map. There are many features on this map. Red is dynamically up, blue is dynamically down, that we know about already. For example, the Iceland plume, which I'll mention at the end, the dramatic drawdowns of the Argentine abyssal plain and this region between Australia and Antarctica. Now, you can weave a spherical harmonic representation of this map, which is what we did out to spherical harmonic degree 31. And the key point is spatially, this is a busy map. There's a lot happening right down to wavelengths of about 1,000 kilometers. This differs from many, but not necessarily all, computational dynamic topographic maps, which tend to be much more long wavelength, much more spectrally red. By and large, there is a considerable difference between the power spectrum that our observations yields, which is the red line here, which is approximately wave number to the power of -1, and a suite of computed dynamic topographic models. I think this is an average of 6. So there's a big difference here, especially at degree 2, where we see an order of magnitude less observed dynamic topography. And at high degree, we also still see a lot of power. These are major discrepancies. And this is a fast-moving topic. How to resolve the models and the observations is still work in progress. So for now, I'm going to focus on the fidelity of the observations, which I think should guide us. So what I really want to talk about is the way in which what you see in the oceans helps to interpret what happens on adjacent continental passive margins. Now, the continents are much more complicated in terms of vertical motions than the oceans, but you can use the oldest ocean floor that sits against continental margins to give you what we call in English informally a leg up or a guide to what's going on. We can see things in the sequence stratigraphy of the margins that links back to the anomalies on the old ocean floor. And then there are other things that I won't have time to talk about, such as heat flow anomalies, magmatism, and the link with fluvial landscape growth. But I'm basically in these 3 stories I'm going to tell you of 3 different case histories. We're essentially going from the marine. We'll go sort of amphibious onto the margin. And then, of course, this leads us onto onshore as well. So the 3 examples are, first of all, an example of dynamic up from West Africa, an example of dynamic down from the Northwest Australian margin, and then a much more complicated North Atlantic story, which seems to be bouncing up and down. Now, I only have time to mention these 3 examples. There are many other examples of up, down, and up and down that I could show you. And basically, we're seeing a pattern across the world. So let's start with West Africa. So I'm going to show you a cross-section along the oldest ocean floor from equatorial New Guinea all the way down to South Africa. So we're looking along this lazy dashed line where you can see that there's a lot of dynamic up and down of the ocean floor. We're particularly interested in this region here, offshore Angola. So here's what the cross-section looks like. And what you note is that the old ocean floor, which is essentially Cretaceous in age, that abuts the continental margin, is extremely bouncy. It's like a waterbed, bouncing up and down with this wonderful quasi sinusoidal oscillation here. Now, we're on ocean floor, the old ocean floor against the margin. I want to take you into the page, like Alice, and we're going to look at what happens if we go through the page here. So I'm going to take you to a seismic line that's much closer to the coastline in the middle of where this positive residual depth anomaly sits. So this is the seismic line. This is quite an old line, but it's very good quality. And the first thing I want you to notice, well, 3 things I want you to notice. First of all, you need to dial out the water bottom multiple, which I'm pointing at right now. Second thing is that there's a truncation of Pliocene stratigraphy at the seabed. So basically, we have 4 sets that are truncated, no top sets. The third thing to notice is this dramatic change, where I'm pointing now, from aggradation below to progradation above. So salt down here, this is a rifted margin. We're in the thermal subsidence phase, but there are dramatic things going on in terms of uplift and tilting. So 2 phases. And the 2 things that happen at the white arrows, there's a major tilting and doming of the margin. And this is in the Oligomycene at about 25 million years ago. And then the final thing that happens is the whole thing is retilted and all of the top sets are truncated to leave you 4 sets against the seabed. So if we go further in onto the actual coastline, there's a lot of good French work from some time ago that shows you that there's a flight of sometimes marine terraces through here, including the Tyrrhenian. And this flight of terraces talks to regional uplift of the margin. So Gouraud et al. Correlated datable terraces on this margin with a series of high stands and still stands in sea level. And the rate of uplift of the margin is a rather heady 0.3 to 0.4 millimeters a year. This margin is going up very quickly indeed. So a cartoon summary of what we think is happening in this offshore Angola region is this was a continental margin minding its own business. It rifted back in the Aptian Albion, and then you had essentially thermal subsidence, which often takes the form of large deltaic deposits. Some time ago, probably at the start of the Neogene, we think a pod of asthenosphere was emplaced beneath the lithosphere, and that creates anomalously shallow ocean floor out here, and it also creates the uplifted and eroded deltaic deposits and the marine terraces. Further on shore, I don't have time to talk about the way in which the river profiles have responded to this uplift, but they have responded to it in a two-phase way that agrees with the two-phase history that we extract from the sequence stratigraphy. Now, some of you are probably thinking...
10 minutes now.
Thank you. Some of you are probably wondering, it's all very well invoking upwelled asthenosphere, but how do we know it's actually there? Well, we can see it. So if you look at panel C on the right here, this is from Schaefer and Lebedev, and it's a slice through their surface wave tomography at about 150 kilometers depth. And there's the low shear wave velocity anomaly associated with the Angolan dome. So that's kind of the proof of the pudding. So the second example I'd like to tell you is from Northwest Australian margin, and this is the other way around. So we're up here, and I'm going to show you stratigraphy from this pink box. The ocean floor immediately offshore is now down by about 700 meters. And what you see in the pink box, where there's some splendid PGS 3D data, is a big carbonate reef deposit. And the key thing about this carbonate reef deposit is you can see that the carbonate facets, the clinoforms proceed outwards, they prograde outwards, and then at this point in time, which is about 10 million years ago, you get rapid aggradation. So it's kind of the opposite of what we saw on the African margin. This is not used to see. The aggradation you see here at the end is far too big to be glaciostatic. Harold Charnota, working with me, tracked out these clinoforms. We carefully backstripped and water-loaded the clinoform crests, and you get a water-loaded substance curve as a function of time that's shown here. And basically the bottom drops out of this margin in the last 10 million years at a rate of nearly 0.1 millimeters a year. So in cartoon form, we think what's happening is, again, a continental margin minding its own business with a splendid carbonate reef in pale brown growing at the top. You then get convective downwelling, or an antiplume, if you will, and this is dramatically recorded within the carbonate reef. So the last example, which I'll quickly finish with, is from the North Atlantic Ocean, where we see up and down movements. The North Atlantic continental margins, which are rift margins, are dominated in their thermal histories by the effects of the Iceland plume, which is shown here in terms of residual depths. So we can see the Iceland plume at depth. This is from Fichtner et al., their full waveform tomography, and you can see the Iceland plume in terms of slow velocities with these fingers pointing in different directions. Now, 60 million years ago, before the North Atlantic opened up, the Iceland plume kicked off at about 64 million years ago. And in regions like the red box and many other regions around the North Atlantic, we see evidence for up and down movements, which we can directly link to the fluctuation behavior of the Iceland plume. So we see that this is a vertical slice through some 3D data north of the Scottish margin. And there are these surfaces, which are very faint down here, which you can see if I burn them into your retinas. So you can see that surface there. That surface we labeled flat. It cuts into marine rocks below, there are marine rocks above, and we have terrestrial meat in the marine sandwich. So what you're looking at when you map it out fully, is an amazing transient landscape buried at depth. It's an Eocene landscape, and it records vertical motions, which we carefully reconstructed, which demonstrate these are vertical motions which are transient. They come and go in a couple of million years, and it's up to 800 meters of vertical motion. It can't be glacial Eustacine. And we think it's because the Iceland plume, which is well-known Neogene behavior of pulsation, we think it also pulsed back in the Paleogene. And every time a pulse or a ripple goes underneath the continental margin, you get a little bit of a up and down movement. There are many other landscapes in the same place, but at different positions in the stratigraphy, showing you that the Iceland plume is a repeat offender. So here are two much more subtle landscapes, which when we map out look like this and this. So to summarize that rather speedy overview, an analysis of ancient ocean crust abutting continental margins helps us. It's a guide as to what the vertical motions caused by mantle convection have been on the adjacent continental margins. There are many more examples of the three I showed you here today. So we're seeing that observed dynamic topography varies on quite short wavelengths of down to 1,000 kilometers with amplitudes of plus or minus 1 kilometer. And these observations differ in a significant way to computational predictions. So the point I want to make is, the point of my talk is the fact that dynamic topography strongly influences many things on the continental margin. I focused on the sequence stratigraphy, but it affects all these other things as well. Thank you very much.
Excellent. Thanks a lot. There's time for one or two quick questions. If you have one, raise your hand or type a Q in the chat and you will be handed over the word. Well, you think about one, and then I have one that is a bit burning. The processes that generate the ups and downs, they are very different. Yeah? Plumes going up and then delamination going down. Do you see the temporal footprint of these different processes in your observational methods in the stratigraphy, that they evolve in a different way, ups and downs?
I think I understand you to mean that in terms of the mantle convective processes, we're expecting different rates depending on whether you have convective upwelling or convective downwelling. I think it's, well, you can be guided by convective simulations, but I think in terms of observations, it's still early days. At the moment, we're seeing rates both up and down of order 0.1 millimeters a year, which is pretty fast. But I'm not sure if we can measure things accurately enough from stratigraphy to be able to tease apart whether things go up quicker than they go down. So that's a very interesting and important question, but I don't think we have a firm answer at the moment.
Okay. Anybody else? I don't see a question. If that's not the case, we are at 20 minutes, so that's actually where the talk is supposed to be ending. So thanks again, Nicky. If someone has a question, please type it in the chat. I'm sure that Nicky will be happy to answer it in the chat.
Or you can send me an email later.
Excellent. Thanks.